to turn on my microphone. There we go. Okay. My mission was to turn on my microphone. That mission is now successful. So my mission was to talk about physics beyond the standard model at the TeV scale. And obviously, I spent a lot of time talking about the hierarchy problem. And that's purely because, if you just want to ask, of all of the problems or hints of something else beyond the standard model, all of them can live or be solved or explained by physics across a variety of mass scales. And there's really only the one, because really you have to explain a scale that's parametrically separate from many others. So it's really only the hierarchy problem that really singles out the TeV scale as a place where signs of new physics should be living. But there are lots of other problems or hints of extensions of the standard model. And unlike the hierarchy problem, which is a speculative problem, right? Again, it's really a problem of our theoretical expectations confronting what nature has given us. It's not a problem of an actual discrepancy in the standard model or a disagreement with the fundamental rules of quantum field theory, right? It's nothing that serious. So you might say, look, that's a great problem, very motivated by the TeV scale. I don't care. I'm not worried about conflicts between our expectations and nature. I would like to think about problems that I could be more confident are real problems, right? That maybe there's a suggestion that there's something there that gives me a reason to think about extending the standard model. So that's a very good reason. I don't want to pretend that this is the only problem we're thinking about. There are more robust things to think about in the sense that we have more evidence for them. So what I want to spend this lecture doing is moving up this chart a little bit. I have nothing useful to say about solving the cosmological constant problem, certainly not at the TeV scale, so we're just going to skip that. But then I just want to spend a little time down here. So I know you've spent a lot of time hearing about dark matter and neutrino mass. You've even heard a bit of time hearing about the strong CP problem in the context of axions. But hopefully I have some new things to tell you about the strong CP problem. And then I just want to talk about unification and baryogenesis. These are things where we at least have suggestions in the data that there's something going on beyond the standard model. And the real question is to see how we can connect all of these ideas to physics at the TeV scale. Okay. So again, these problems could be solved with physics across a range of mass scales. But what I want to convince you of today is that there could be interesting solutions that live near the TeV scale. And they're interesting to think about, and they're interesting to look for. So these are things, they certainly don't have to happen in nature, but they're opportunities and reasons to start asking interesting questions. Okay. So the strong CP problem, you've already heard, of course, quite a few lectures about axions and dark matter, so I think you know what the problem is. I just want to remind you of it in the language that we've been using so far of naturalness and technical naturalness. Okay, so again, the idea is we write down the standard model. If we write down all the marginal and relevant operators, once we acknowledge that CP is not a good symmetry of the standard model, right, that there is CP violation in the weak sector that shows up in the CKM matrix, then there's also nothing that prevents us from writing down a topological term for the SU3 gauge fields. In particular, there's a parameter we call theta or theta QCD that violates CP, and then it's proportional to GG dual. Okay, so this term is allowed by the manifest symmetries that we see in the standard model. And of course, if we write down such a term, we can actually, this just appears in front of the gluon field strengths, and it's dual. But we can go ahead, QCD confines, we get mesons and baryons. We can go ahead and trace the appearance of this term into the effective theory that describes mesons and baryons. And what we find is, right, it gives some effective operator that looks like a dipole moment that couples the photon to neutrons, all right? And it has some coefficient. And that coefficient has a variety of factors in it. It depends in detail on the masses of the quarks. It depends on, of course, the confinement scale of QCD. But in particular, this dipole moment is directly proportional to this theta term, right? That's the origin of the CP violation that induces a dipole moment. Okay, so if this term is non-zero, then there should be some neutron electric dipole moment. All right. Of course, again, we've gone, as you've already heard, we've gone and made lots of measurements of the neutron EDM. We have yet to find anything. So the bound on the neutron EDM tells us this parameter is less than 10 to the minus 10. Now, there's nothing in the context of the standard model, that's a bad violation of our Dirac ideas of naturalness, right? This parameter by Dirac argumentation should be order 1 instead of 10 to the minus 10. So this looks like another issue where we have a small number problem. It's not really technically natural, right, for several reasons. I mean, it's true in isolation that if we set the theta term to 0, there would be no extra CP violation coming from the QCD sector. But because we know that CP is not actually a good symmetry of the standard model, right, in the context of the standard model, CP doesn't become a good symmetry if we set theta equal to 0. So it doesn't really satisfy the criteria of technical naturalness. However, it's sort of in this funny middle ground where if you actually asked if I just write down the standard model and CP violation that I see in the CKM matrix, if I ask how the theta parameters were normalized, the answer is the running, so the quantum corrections to a given theta parameter is very, very small in the standard model, and that's because the quantum corrections have to go through lots of different loops of standard model states to get to the CKM phase. So, you know, it's sort of, its status as how much we should be concerned about it is sort of in the middle ground. It's not formally a technically natural parameter, but if something set this parameter in your fundamental theory, it wouldn't be done, no violence would happen to it, at least in the context of the standard model, as you go to longer and longer distances. Okay, but you know, that's an uncomfortably small number, and so we always like to see if we can explain it more in a more deep way. Okay. So you heard a lot about axions and how they do this, right? The idea of the axion, you arrange some particular elaborate structure where you get an extra goldstone that couples to the topological term in the same way as theta. And then if you just look at the potential for the axion, the minimum of the axion potential is exactly where it cancels off whatever theta term exists in the theory. And so this would be a way to understand CP is not a fundamental symmetry of the theory, but there is a new particle, and at the minimum of its potential, it cancels off this naive contribution to CP violation. Okay, so you've already heard a lot about axions. Axions don't necessarily have anything to do with the TeV scale, so I don't get to talk to you about them more in this lecture. But you can ask yourself a question, okay, are axions the only way to understand the smallness of the CP angle? Excuse me, the QCD theta angle? And the answer is no. So there's another thing you might have had in the back of your mind, which is that certainly I could understand the CP angle being 0 if CP were actually a good symmetry of my fundamental theory, right? If in the far ultraviolet, very short distances, the standard model were actually CP symmetric, okay? Of course, we know there's CP violation in the CKM matrix, so we know that there is CP violation, but maybe what's happening is the fundamental theory is CP symmetric. Then there's spontaneous violation of CP, right, in the same way that we spontaneously break other symmetries. And maybe that spontaneous violation appears in the CKM matrix, just like we see, but maybe for some reason it doesn't show up in the theta term. Okay, that seems like a detail-dependent statement, but it's possible to imagine the theory of the universe working that way, right? That would be a fundamentally different type of solution from the axion solution. The axion solution says, give me as much CP violation as you want, and I will get rid of it dynamically. This would say there's a symmetry reason for the CP angle being small, and then there's just a controlled way of breaking that symmetry to see the CP violation that we know exists in nature. All right, so it's a technically challenging problem. It's not obvious how you would do this for the following reason. So as hopefully you heard in your axion lectures, there's really two contributions to what you think of as the strong CP angle. So I can always write down the theta term in front of the gluon field strengths, but I can do an anomalous rescaling that would move that phase into the phases of the masses of the quarks. Okay, so in reality, there are two possible places to put a phase. They both have the same effects. They're equivalent. So what we normally do is we say, look, there's one physical strong CP angle that actually appears in the neutron EDM, and it's a linear combination of a phase that appears in the quark masses and the phase that lives in front of the gluon field strengths. And I can always change back and forth between them just by doing anomalous rescalings. So they're really just the same thing. Okay. Now formally, all right, so this is the thing that appears in neutron EDMs. This is the thing that appears out in front of the gluon field strengths. This extra piece, the phase that appears in the quark masses, what it is formally is, okay, really, in reality, the quarks get their masses from electroweak symmetry breaking, so it has to be coming from the Yukawa couplings. And the place where the phase actually appears, it's actually the argument of the determinant of the product of the up-type Yukawa matrix and the down-type Yukawa matrix, right? So each one of these is a 3x3 matrix. I take their product, I take the argument of the determinant of that thing that picks out the overall phase, and that is the phase that is on the same footing as the phase that appears in front of the gluon field strength. Okay. So what is the challenge? The challenge is we know this is small, right? This is what we measure in the neutron EDM. This is what we've bounded to 10 to the minus 10. So loosely speaking, that tells us that both of these things are small. There's no reason why they should be equal and opposite, because I can always move them back and forth. So both of these guys should be small. So if I want a spontaneous CP violation, if I want to have CP be a good symmetry in the ultraviolet, I want it to be spontaneously broken. I want CP violation to show up in the CKM matrix where I know it exists and I've measured its size, but I don't want it to show up in the neutron EDM. What do I have to do? I have to have a CP violation in my model so that this term, right, the argument of the determinant of the product of the Yukawas, which appears here, this term has to be small. But I also have the observed CKM phase. If I write it in the same language, the observed CKM phase I can pick out of the Yukawas by taking the up-type Yukawas times the down-type Yukawas minus the down-types times the up-types, right? That's also a matrix. If I take the argument of the determinant of that, that actually picks out the CKM phase. Okay, that's a nice way to write the CKM phase in terms of the Yukawa matrices. All right, so this has to be big. If I violate CP spontaneously, this has to be big, this has to be small. Just looking at the two things, it's not obvious how I would do this, right? I need the difference between, I need the commutator of these matrices to have a large phase in it, but I need each term, the product itself to have a small phase. All right, so that seems very hard. Naively, you would look at that and give up. But of course, you know, that's really just a challenge, so it's time to go to your office and build a model. Okay. So there's a long history of model building for spontaneous CP violation. Most of the ideas pursue this direction that I told you, where CP is a good symmetry of the fundamental theory, and then it's spontaneously broken. So these models are all generally called Nelson-Barr models, primarily after Ann Nelson, who was the first to really work out the details of how this had to work. But there's actually an alternative argument that works along similar lines. And the reason why I don't want to talk about Nelson-Barr models, but I want to talk about the alternative is Nelson-Barr models are pretty complicated. It's a little hard to see what's going on. And it doesn't necessarily connect to physics at the TeV scale. But there's an interesting argument for the alternative. Okay, so what's the alternative idea? I could understand why the theta term is 0 at high energies, not necessarily by making CP a totally good symmetry of my theory, but just by making a parity a good symmetry of my theory. Right? It's enough if I have a parity, which changes the sign of the theta term. If parity is a good symmetry in a generalized sense, then I can explain why theta is 0, and then I have to break the parity in a special way to get the CKM phase. Okay. So what's the idea? So this idea, the first model of this kind was written down in part by Barr, but in part by, of course, a former member of the ICTP faculty, or excuse me, a retired member of the ICTP faculty. So the idea is you extend the standard model with the parity. So we have the standard model, it's SU3, SU2, U1. We extend it by introducing a new SU2, so let me call that SU2 prime. And now, in addition to all the fields of the standard model, right, that have the normal charges, so they, under this extended theory, they have their normal charges under the normal SU2. And if we add a whole mirror copy of the standard model that has the same quantum numbers as standard model fields, but is charged under the new SU2 instead of our original SU2. Okay, so that's all we do, right? So we add this new SU2, we add a whole copy of standard model matter that's charged into this. Everything else, all of our normal standard model matter is charged under the first SU2. All right, so this theory has a generalized parity symmetry. So the parity symmetry in this theory, it acts like normal parity does, okay? So in particular, under normal parity transformation, theta goes to minus theta. But this parity transformation also acts on the two SU2 factors. So it swaps basically everything, it swaps the first SU2 with the second SU2. So in particular, it sends all normal standard model matter, which is charged into the first SU2, it sends it into the second SU2, all right? And it also sends the mirror stuff back to the first SU2, okay? So it's a generalized parity symmetry. It acts like normally parity does, plus by swapping these two SU2s. All right, so if this is a good symmetry of the theory, if this parity symmetry is a good symmetry of the theory, it explains why theta is 0, because theta just appears in the SU3 sector. Theta flips sign under these parity transformations. So if the parity is good, theta is 0, we're happy, right? Now, the parity also swaps, again, the fields charged normally like the standard model with the mirror copy. So you can ask what conditions that might impose on the Yukawa matrices of the matter multiplets in the standard model and their mirror counterparts. And the answer is, okay, you can take the standard model Yukawa couplings, for example, the up-type Yukawa matrix, right, which couples the Higgs to the up-type quarks. You can also take its counterpart in the SU2 prime, the mirror counterpart, so that's some new matrix with all the mirror fields. this parity transformation, right, it swaps the fields with their counterparts, but also, of course, the parity transformation flips the sign of any complex phases. And so in particular, if there are phases that live in the Yukawas, the parity transformation is going to flip those. So making these Yukawas invariant under the parity transformation, it forces the Yukawa matrix of the mirror fermions to actually be the complex conjugate of whatever the Yukawa matrix is for the standard model fermions. Okay, this is, if the P is a good symmetry, that's what it enforces on the Yukawa matrices. So that's pretty interesting. The reason it's interesting is the combined set of phases, so for our fermions and the mirror fermions, they're all charged under QCD. So a phase in either our Yukawas or the mirror Yukawas, both of those could be fed into the strong CP angle. So the phase that appears in the quark Yukawas that would give us a strong CP angle is actually the combination of argdet of our Yukawas, right, which we saw before, plus the argument of the determinant of the mirror Yukawas, right? That's the combination of phases in the Yukawas that would feed into a neutron EDM. But because these Yukawas have to be the complex conjugates of the standard model Yukawas, right, by the parity symmetry, in the sum of these things, the argument of the determinants of that sum is 0. Okay, so basically what's happened is whatever phase lives in the argument of the determinant of the product of our Yukawas is canceled by a corresponding phase in the argument of the determinant of the mirror Yukawas. But that means the phase living in this product of Yukawas can be large, right? So the thing that gives us the CP angle in the standard model with standard model fermions is still just this combination. This can be big, but the combination that appears as a phase for the neutron EDM is this combination, and this combination is exactly 0 by the parity. Okay, so we have a beautiful way of explaining, right? And now, of course, this also, the implication of this is the CKM phase in the mirror sector is the opposite of our CKM phase, but we don't measure that, so we don't care. All we care is we haven't seen the neutron EDM, and we see a CKM phase in the Yukawas. All right, so this hopefully tells you there's a way of explaining, parity can be a good symmetry. You can use it to explain why the neutron EDM is small, and you can use it to still understand why there's a CKM phase that we measure in nature. All right, pretty cool, right? A little different from axions, okay. Now, of course, if this parity symmetry were exact, we would see all of these mirror quarks charged under SU3 and hypercharged. They're just charged under this different SU2, right? So it has to be, this parity symmetry observationally can't be a good symmetry of nature at low energies. It has to be spontaneously broken. Again, it's a good symmetry at high energies, so it helps us with all of our phases. But we have to spontaneously break it to just explain the fact that we haven't seen these fields at low energies. Okay, so there's various ways to do that. One is to say, let me add some new scalar to my theory that's odd under parity transformations, okay? So if it's odd under parity transformations, it would couple to the difference between our Higgs and the mirror Higgs, right? This total combination would be invariant under a parity transformation. And now if this thing gets a vacuum expectation value, because it's parity odd, that should spontaneously violate the parity symmetry and allow us to understand maybe why we don't see these extra mirror fermions. All right. Now you might think, look, I can just make the vacuum expectation value of this field super big, right? I can violate parity at high scales and just erase any evidence that this theory ever existed, except for these funny pattern of CP violation at low energies. Okay. So you might do that, but as an effective field theorist, right, you have to pause and think for a second. And one thing you have to think is, well, look, I know the standard model is only an effective field theory. I know I should have all the higher dimensional operators involving combinations of my fields. And the scale, the largest scale that could suppress these operators is maybe the scale of quantum gravity, is the Planck scale. So that means generically I would expect parity, allows me to write down a term that couples this new parity odd field to parity odd combinations of the gauge field. So in particular, the symmetries allow an irrelevant operator that couples that parity odd field to GG dual. And maybe that's suppressed by something like the Planck scale. So that operator should just generically be there in my theory. It's invariant under parity. It's just an irrelevant operator. Okay. So now, of course, if this scalar phi gets a vacuum expectation value to break the parity, then generically, right, when it gets a vacuum expectation value to break that parity, if its VEV is too big, In particular, if its VEV is within 10 orders of magnitude of the Planck scale, it gives me an effective theta angle that appears in front of GG dual, right? And that would reintroduce a strong CP problem. It would give me a new theta angle that's not protected, that's just generated by this irrelevant operator. All right, now generically, when you write this down, if phi got a big VEV, you would also end up moving around basically the potential for R Higgs and this parity copy of the Higgs. And the vacuum expectation value of the parity copy of the Higgs would be about the same size as the vacuum expectation value of phi. So that tells you the VEVs, both of this thing that breaks the parity and the Higgs and the parity mirror copy of the standard model, neither of these scales can be too far, too close to the Planck scale. If they were, then we would have new sources of CP violation that we don't see. Okay. So that puts a bound basically on the scale of spontaneous parity violation. That puts a bound on the scale of spontaneous symmetry breaking in the parity copy of the standard model. And that tells us we can't make those states arbitrarily heavy. All right. But that's pretty cool, okay? Because if we've bounded the breaking of parity to be 10 orders of magnitude below the Planck scale, just to not make too big of strong CP, that also bounds the vacuum expectation value of the Higgs that couples to the mirror fermions. All right, so that therefore it bounds the mass scale of all the mirror fermions. Now, 10 orders of magnitude less than the Planck scale is still 10 to the 8 GeV, right? So the mirror version of the top quark can be at 10 to the 8 GeV. That's inaccessible. But we also know there's a 5, the parity exactly relates to the Yukawa couplings. And we know there's a 5 order of magnitude difference between the top Yukawa coupling and the electron Yukawa coupling, right? So if the mirror top is at 10 to the 8 GeV, then let's see if I can do the math in my head. The mirror Yukawa had better be to TeV. Excuse me, the mirror electron had better be to TeV because Yukawa is so much smaller. Okay, so that tells us, right, the first generation of fields that are related by this parity solution of these mirror fermions, once we've learned that the breaking scale of the parity can't be too high, that tells us all of these fermions, so the mirror up quarks, the mirror down quarks, and the mirror electrons, they should probably actually be around the TeV or 10 TeV scale. Okay, so now you see how we come back to physics beyond the standard model at the TeV scale. We tried to solve the strong CP problem. We did it by introducing this new parity, all right? But now we see, just by consistency of the model, as effective field theorists, we have to have some new particles that show up around the TeV scale. Now, that's just a numerical coincidence, but it's a pretty interesting numerical coincidence because we happen to be able to probe the TeV scale experimentally. Okay, so the details of what happens, that means you have these new fields that are light around the TeV scale. Okay, remember, they were charged under the other copy of SU2, but they're still charged under SU3, and they're still charged under hypercharge. So these things have standard model charges. We can produce them in proton-proton collisions. Exactly what they do when we produce them depends on some more details, what other couplings couple those things to their parity counterparts. But generically, that predicts new states that have standard model quantum numbers, and if we produce them and they can decay, they decay into standard model stuff. So generically what they look like, for example, these mirror quarks, depending on their couplings, if you produce them through their QCD charges, they can decay to standard model quarks plus standard model bosons. All right, so these are generically ways that if you produce these new parity counterparts, these guys can decay. And you might notice, so when we talked about global symmetry solutions to the hierarchy problem, we said we predicted lots of new fermions, right? In fact, these fermions that were the partner particles of standard model fermions, and they also all were produced and decayed in this way. So here's a solution to a totally different problem, right? This is a solution to a strong CP problem. Has nothing to do with the hierarchy problem, but it predicts a new spectrum of states at the TeV scale that look a lot like the type of states we predicted when we were trying to solve the hierarchy problem with global symmetries. Okay, so we have lots of searches for particles of this form at the LHC. We're definitely looking for them. All I really want to emphasize to you is trying to solve a totally different problem in the standard model sort of leads you to think about very similar states that you thought about when you were trying to solve the hierarchy problem. All right. Okay, of course, no one has to, nothing in the universe guarantees that this is how the strong CP problem is solved, but it's a very interesting suggestion of one way that it might work. All right, let me shift gears entirely. So that was all I wanted to say about the strong CP problem and what evidence you might have for its solution at the TeV scale. So let's move to one of the next suggestions that we have for physics beyond the standard model. And this suggestion is more substantial, right? Strong CP problem is like the hierarchy problem. It's the problem of a small number that we don't know how to understand in our quantum field theory, and maybe nature doesn't care about those sorts of problems. Unification is a bit different. Unification, we at least have a suggestion based on the combination of measurements we've made at the weak scale and the consistency of our quantum field theory that something interesting is happening at short distances. Okay, so what's gauge coupling unification? Again, we sort of started out all of our lectures talking about it, so now let's come back to it. The idea, again, is just that we measure the standard model gauge couplings down at the weak scale. In particular, the LEP measurements at the z-pole give us very high precision. And then if we just have the standard model up to some very high energy scale, we know how these couplings change as a function of scale, right? We just write down the renormalization group equations for these couplings. So in this case, we're writing down the renormalization group equations for alphas, which are the squares of the couplings over 4 pi. Okay, so those are the RGEs, tell us the evolution of the couplings is determined by the beta functions. The beta functions we can compute in whatever order we would like. So at one loop, they have a nice simple form in terms of the beta function coefficients of the standard model. Okay, so at one loop, we can actually solve these RGEs. And again, it just tells us if I've measured one of the standard model gauge couplings at the weak scale, then I can figure out what the coupling will be at some higher scale just by solving this differential equation. And at one loop, the solution has a very simple form. Okay, it just has a logarithmic dependence on the energy scale. And the coefficient of that logarithmic dependence is the beta function coefficient. All right, so if you do that in the standard model, here I'm plotting 1 over the alphas, okay? So in 1 over the alphas, QCD starts out down here, SU2 starts out up here, hypercharge starts out up here. This is where we measure them at the weak scale. Now we just solve the RGEs, and we see what they do as we go to higher scales. Okay, so pretty suggestive. They all seem to group together at one scale. It's around 10 to the 15 GeV. Now, you shouldn't be too impressed by this, because if I have 2 lines, as long as they're not parallel, they're going to cross at some point. If I have a third line, as long as it's not parallel to the other 2, it's going to cross the other 2 at some point. It's not obvious that these are all crossing in a very close place, but okay, we're human beings. We find patterns in all sorts of random crap. All right, so this has been a suggestion for a long time that maybe something happens to the couplings up here. And we already know it would be nice if something happened here, because if we kept running hypercharge, hypercharge would eventually blow up. All right, so the intersection, the mutual intersection of these couplings is around the 10% level at 10 to the 15 GeV. And it's at least consistent with the idea that the 3 gauge couplings of the standard model, or the 3 gauge groups, SU3, SU2, and U1, might unify into a single simple group with a single gauge coupling. Okay. Conveniently, of course, Howard Georgi realized back in the day that you could conveniently fit SU3, SU2, and U1 in either SU5 or slightly more complicatedly, you could fit it into SO10. All right. In fact, I think he discovered SO10 first and then worked his way back to SU5. Both of these would be simple groups in which you could fit the standard model gauge groups. All right. So it's a convenient and beautiful fact that, of course, if that's really what happens, right, if the standard model gauge couplings unify at some scale, we'd also better be able to group all of the matter representations of the standard model into irreducible representations of the unified symmetry. All right. So conveniently, that works out pretty well, right? So here, what I've tried to do is plot, all right, let's imagine that all the standard model forces unified into SU5. Then we'd better be able to fit all the standard model fields into SU5 representations, okay? So something that transforms as a fundamental of SU5, if you decompose it under the standard model gauge group, that's a subgroup of the SU5, then what you find is, for example, if you took a scalar transforming in the fundamental that decomposed into these appropriate standard model representations, it would transform like some triplet of the standard model gauge groups, in particular a triplet of SU3 with hypercharge, and it would also transform like something that has the quantum numbers of the Higgs doublet. Okay, so we could certainly fit the Higgs into a representation as long as it comes along with the triplet partner for the ride. We started with the anti-fundamental of the SU5, all right, that decomposes in a similar way, but we recognize these quantum numbers correspond to the quantum numbers of the right-handed quark, so the SU2 singlet quark, down-type quark, and also to the SU2 doublet lepton, right? So we can fit quarks and leptons together into the same representation, all right? Similarly, if we start with the 10 representation of SU5, we decompose that, we find we get 3 representations, and those conveniently, of course, fit the remaining fermion representations in the standard model. So between the anti-fundamental and the 10 representation of SU5, we can fit a single generation of standard model fermions. And then the Higgs just has to come along with some extra buddy to fill out a complete representation. So this is very suggestive, right? This at least blows my mind a little bit, even now when I look at this, right? Is that you can, a single generation of standard model fields with all of their random charges, right, which looks like someone picked them out of the hat. They are precisely such that they fit beautifully, cleanly into simple, clear representations of a unified group. All right, so that's very suggestive. Again, the lesson for particle physics might be that all of these suggestions are just accidents, but I would like to think this is a sign of something deeper. Okay, you can do the same thing with the gauge fields. Of course, gauge fields in the standard model transform in the adjoint representation, so you can fit them all together to transform in an adjoint of SU5, and you get along for the ride 2 extra gauge fields that transform in sort of mixed representations under the standard model gauge group. Okay. All right, so standard model fits nicely into unified representations of SU5. The only price we pay is we have to bring along an extra triplet scalar for the ride, plus these new gauge bosons. Okay, so it's a beautiful idea. In fact, the original notion of naturalness in particle physics, the first place where people really started to try to apply it was not technical naturalness or any of those things. It was actually the idea that a complicated theory should fit into a simpler theory, right? That also seems like an idea of naturalness. And unification was really the first place people tried to do this, right? Complicated theory, the standard model, all these random charges, fits into a much simpler theory, just a few representations of a simple gauge group. Okay. What are the bad parts, right? Okay, unification of couplings is imperfect, right? It's only about the 10% level, so there have to be some finite corrections to make these things agree a little bit better. If I unify all the standard model fields into uniform representations of SU5, I also do the same thing with the Yukawa couplings. So that gives me predictions for unification of Yukawa couplings that are not necessarily in good agreement, right? The Yukawas don't fit a nice pattern coming from simple unification. And finally, I have these new extra fields that carry various quantum numbers of the standard model. And in particular, the couplings of these fields actually violate baryon and lepton number. They violate some of the nice accidental symmetries of the standard model. And if you violate baryon and lepton number, then exchanging these particles means you can make the proton decay. Okay, so predicts proton decay. So now we decide how much of a concern that is. Okay, so let's think about the proton decay a little bit more. All right, I'm going to ignore this side because it is a little model dependent. So let's just pay attention to this side, which is model independent. So we have these new gauge bosons, right, from fitting the standard model gauge bosons into an adjoint of SU5. These things now, their couplings to standard model fields are given naturally by the couplings in the SU5 theory. So in particular, they mediate interactions, for example, between a lepton and 3 quarks. And if we integrated out these gauge bosons to make an effective 4 Fermi operator, right, that would correspond to the physics at much lower length scales, it would be these irrelevant operators, right? So here again, we see some more dimension 6 operators involving standard model fields. These operators violate baryon and lepton number, okay? And they're suppressed by some scale, and that scale corresponds to the mass scale of these new gauge bosons, the mass scale of unification. All right. So we actually know in this, here's a case where, okay, we could randomly write down these operators, right, in the standard model EFT. We could write them down and ask what the coefficient is. But the hypothesis of unification gives us a prediction for what the scale should be, right? It tells us the scale should be around 10 to the 15 GeV. So we predict now these operators should exist with a scale of 10 to the 15 GeV. Okay, sounds good. Unfortunately, right, these operators violate baryon and lepton number. So what do? Well, they give proton decay, right? So how does that go? So here's a proton flying around with its valence quarks. Now I can take the 2 up valence quarks, can use one of these heavy gauge bosons to turn it into a lepton and a down type quark, and that will give me an electron, or it's going to give me a positron and a neutral pion. Right, so the proton decays now, and you can go ahead and you can work out the rate for this decay, or the lifetime of the proton, all right, given these operators, and it's on the order of 5 powers of the proton mass over 4 powers of the gut scale, so that's about 10 to the 29 years if the unification scale is 10 to the 15 GeV. Okay, so this was actually a great prediction when people first wrote down unified theories, right? We didn't know that the proton was stable to that length. That's way longer than the lifetime of the universe. So then, of course, they built a lot of Cherenkov detectors, Kamiokande being a beautiful example, started looking at large volumes of water for long periods of time, And we've gotten, since the first unified predictions, we've gotten up to bounds at super Kamiokande that are approaching 10 to the 34 years, right? So orders of magnitude tighter bounds than what we predict. So this naive picture of unification has been falsified. Now, thankfully, luckily for us, detectors like Kamiokande also turned out to be good for detecting neutrinos. So it's okay if the proton isn't decaying. We still get to get other physics out of it. But their first purpose was to falsify this assumption. Okay, so the vanilla assumption about unification just is ruled out by data. All right, so we could give up and go home. That might be attractive, especially at the end of this long summer school. But you can ask, okay, all right, is there any slight distortion of this picture that would make the unification hypothesis compatible with current data? All right. So you can ask, look, we came up with these unification ideas by just taking the standard model fermions and using those to run the couplings up. But of course, if I had new particles that were charged into the standard model, that would change how the standard model couplings ran, and it might cause them to intersect at a different point, right? They might intersect at a different energy. And if they intersected at a higher energy, the proton decay rate goes like 1 over 4 powers of the unification scale. So if I raise the unification scale by 1 order of magnitude, I change the proton lifetime by 4 orders of magnitude, right? So I very quickly can make myself compatible with the current bound from super Kamiokande. All right, so how would it go ahead and work? Well, if you just added some new fields at some mass scale, so let me call it m psi the mass scale, I'm going to assume they're fermions because, as you probably know from calculating beta functions, scalars pay an unfortunate extra suppression factor relative to fermions. So fermions are really somewhat more efficient at changing beta functions. All right, so if we imagine adding some new fermions that are charged under the standard model at some new scale, okay, it'll change the running of all the gauge couplings, and you can go ahead and again solve the one-loop beta functions. And so you'll find if you've measured the couplings at the z pole, which is where we've measured them, then of course they're running up to the unification scale. It has the standard model piece that we've already been thinking about, and now there will be a new piece that's proportional to whatever the representations are of the fermions, right? That changes the beta function coefficients. And the logarithm, they're contributing only between their mass and the gut scale, right? So the particles only contribute when they run in loops. So if they have some large mass, they're not going to contribute down at the weak scale, but they will contribute once we're at energies above their mass. Okay. So the logarithm is not the log of the z pole up to the gut scale. It's the log of whatever their mass is up to the gut scale. Okay. Now, if we just added something that shifted the SU3, SU2, and hypercharge gauge the beta function coefficients by the same amount, actually, if you look at this, it wouldn't shift the value of the unification scale. M gut would still be the same place, around 10 to the 15 GeV. All it would do would actually be to shift the values of the couplings where they unify. Okay. So if I shift all the beta function coefficients by the same, I'm just translating the couplings. I'm not actually changing where they intersect. All right. But if I introduce matter that gives different changes to the SU3, SU2, and U1 beta function coefficients, that will then change where the lines intersect. So that would actually have the effect not just of changing the value of the unified coupling, but changing the point where the lines cross. All right. So you can go ahead and make yourself a table. This is from a table by Giudice, Rotazzi, and Strumia, which has the delightful name. Am I allowed to repeat the name in public? No, you're not going to. Am I being filmed? I'm being filmed. Okay. The paper has the delightful name of Unification. So what they did, right, is they just asked, okay, if I imagine adding new representations with various charges in the standard model, all right, each one of them, they chose various representations which I could fit together with some other things to form unified representations. But if I just added one of these individual representations with standard model charges, then each one of those I could work out what is the change in the standard model beta function coefficient. Okay, so for example, I could add something with the quantum numbers of the right-handed down-type quarks. Then that would change the QCD and the hypercharge beta function coefficients by some amount, and it wouldn't change the SU2 coefficient because they're not charged under SU2. So you can make a whole table of all these things. They all change the running of the standard model gauge couplings by some amount. And now you can ask, okay, if what I want to do is make the unification scale higher by an order of magnitude, and maybe also improve the precision with which the couplings cross, then some of these new representations, right, are going to help me to do that. And their mass scale, where they show up, will be set by trying to improve the unification of couplings and push up the scale. Okay. So So here's a plot in the space of the changes, the relative changes in beta function coefficients. So how much a matter field changes the QCD beta function coefficient versus the SU2, and how much it changes the SU2 versus hypercharge. So you can take all of the matter representations on this table, and you can plot them in this space, right, by how much they're changing the relative beta function coefficients. So they all lie all over the place. They're all changing things in different directions. And then you can say, okay, so that's one thing. That's where all of these representations lie, how they change the beta function coefficients. But you could also just say, if I wanted to improve the precision of gauge coupling unification, make the lines cross closer together, and if I want to push up the scale at which they do that, I can look at, again, in this plane and changes in beta function coefficients. And I can ask, okay, where do I want to be in this plane to push up the gut scale and to improve the precision of the unification? And so the way it works in this plane is you improve the precision of the unification as you go up in this direction, and you raise the gut scale as you go up in this direction. Okay, so you sort of want to live, in particular, the way this plot works, if you want to have relatively small changes in the beta function coefficients, if you want to get a good scale of unification, like 10 to the 16 GeV, consistent with the proton lifetime, and pretty good precision on the unification of couplings, you would want to live somewhere around here. Okay, so that point is about, what, -0.5, 1. Okay, so if I go over here, -0.5 is like here, 1 is up here, so there's just a few representations. Excuse me, sorry, -0.5 is over here, 1 is up here, so there's just a few representations that would do what I want in terms of pushing up the unification scale, consistent with the proton lifetime, and improving the precision of my unification prediction. Okay, so you can go back to this table, ask which representations might do that, and there are two representations that pop out. So one of them is this representation L, all right, and one of them is this representation Q. They both live in this place that improves the unification scale and the precision of my couplings. Okay. So now you can ask, what are the quantum numbers of these fields that help make unification work much better? Well, the quantum numbers of this field L, they're the same quantum numbers, right? This is some new pair of fermions. They're actually vector-like fermions. And they have the same quantum numbers as a fermionic version of the Higgs and its vector-like counterpart. Okay, so from our discussion of supersymmetry, right, those are the quantum numbers of the supersymmetric counterparts of the Higgs, right? Those are the Higgsinos. Okay, so this is one reason why people have been enthusiastic about supersymmetry, is supersymmetry actually gives you for free the new particles that would help to improve unification. But if you didn't care about the hierarchy problem, right, if you don't care about the hierarchy problem, but you just think the unification is interesting, you would still say you expect to see new fermions, right, who maybe have the quantum numbers that are the same as the quantum numbers of Higgsinos. And to get all these things to work, to improve the unification prediction, the precision of the crossing, you also need the mass scale of these fermions to be relatively low, because that's feeding into the logarithm here. So you get a good prediction if the mass scale of these fermions is around the TeV scale. Again, has nothing to do with the hierarchy problem. It just has to do with getting a nice prediction for unification. Okay, similar thing works for the Q fields. The Q fields have the same quantum numbers as vector-like quarks, which we encountered in the global symmetry solution to the hierarchy problem. And again, in our parity solution to the strong CP problem, those things again show up as helping with your unification prediction. All right, so that's pretty cool, right? What this tells you is unification, so forget the hierarchy problem, forget anything else, but all of those particles that we kept running into when we were trying to solve the hierarchy problem, they also show up related to a totally different question in the standard model, which is, how would I want to extend the standard model so that the suggestive hint of gauge coupling unification would both, one, be more exact, and two, be consistent with what we know about the proton lifetime. And what it tells you is you could expect to see new fermions, vector-like fermions, whose mass scale is around the TeV scale. All right. It's not surprising that it works this way, right? Unification is something that's going to happen at a very high scale, 10 to the 16 GeV. But because couplings run logarithmically, just like the logarithmic running of the QCD coupling gives us dimensional transmutation, the logarithmic running of all the standard model gauge couplings tells us that if we want to add new particles to the standard model to improve our unification prediction, we should be adding them at a scale that's closer to the weak scale. All right, so that's pretty cool. Different motivation for physics beyond the standard model, still predicting interesting new states. Okay. All right, so that's all I wanted to say about unification. So let's turn to the last major problem or suggestion for physics beyond the standard model, that you haven't been talked at during the summer school? Actually, has anyone talked about baryogenesis at the summer school so far? Yes? No? Yes? Okay, you've heard about baryogenesis. Okay. What did you hear about baryogenesis? Nothing? Oh, that it would happen, that it has to happen? Okay, all right, good. Well, let me build on whatever Yossi told you, right? So presumably he told you this statement, okay, the universe is made of baryons, not antibaryons. That's an interesting observation. Quantitatively, you can ask, what is the difference between the number density of baryons and antibaryons? You need to normalize it to how much stuff there is in the universe. So we normalize it to the number density of photons. And so this ratio, right, this is characterizing the amount of the asymmetry between baryons and antibaryons. The number is on the order of 10 to the minus 9. Now, that's an interesting observation. Okay, so as physicists, we would like to explain that number, but in fact, it's sort of a deeper thing that we have to explain because modulo the CP violation that we see in the standard model, otherwise our fundamental theory treats baryons and antibaryons in the same way. So something has to happen to treat baryons and antibaryons differently so that we end up with more of one and less of the other in the universe, right? So this is just a statement, this is something we measure, this is data, right? And because our fundamental theory doesn't explain this data in a nice way, we need to think about it a little more deeply. So that's the sense in which baryogenesis is in some sense a more real problem than the hierarchy problem, right? We have data that tells us there's an explanation that's missing. Okay, so now you might just say, hey, what if I started the universe in a symmetric way, symmetric between baryons and antibaryons, right? So you might think that's a good idea because you've already been hearing, when you heard about dark matter, right, you can put weakly interacting dark matter, weakly interacting massive particles in the early universe. And of course, they're going to be annihilating like crazy, right, when they can. But because the universe is expanding, there's some point in the universe where their annihilation rate ceases to be efficient. And at that point, we say that those things freeze out. So even though weakly interacting massive particles, even though WIMPs are capable of annihilating away if you gave them enough time, because the universe is expanding, eventually they stop annihilating, and we end up with some residual amount of dark matter that we see today, right? So you could ask yourself the question, hey, what if I just started out with the same number of baryons and antibaryons? So they're going to be annihilating like crazy, right, as they can. But if the universe is expanding, maybe at some point, those annihilations become inefficient, and I just end up with isolated pockets of baryons and antibaryons, right? So then I could end up, at least locally, with what looks like some baryon asymmetry. So you can go ahead and repeat the calculation, the same calculation that you do for WIMPs, for the freeze out of WIMPs to give you dark matter. You can do the same calculation for the freeze out of baryons. The mass scale instead is set by the mass scale of the baryons. That's the proton mass. And so you can ask yourself, okay, what's the baryon asymmetry that I might expect to get in local patches if this is what happened, if I started with a symmetric universe between baryons and antibaryons and just let them do their thing? And the answer is, the abundance that you would get, the number densities you get about the point where they freeze out is about 10 to the minus 18. All right, so that's a much smaller asymmetry than the one that we see. So this naive explanation that I just start with symmetric populations and let them freeze out, just like WIMP dark matter, doesn't work. All right, so we got to do something a little bit more elaborate. There's basically three options that we could use to explain this asymmetry. The first, we could just say the initial conditions are tuned. The universe started, and there were just more baryons and antibaryons by this amount. Okay. All right, that's pretty unsatisfying. It could be the case, but it becomes even harder if you think that we had a period of inflation in the early universe, right? Because then the idea would be we started out with some asymmetry that was put in by hand, but then inflation happened, right? And it blew things all sorts of random directions. And that would wipe out any asymmetry that was put in by hand, okay? It would wipe it out exponentially. So there's really no way to understand starting the universe with an asymmetry, having inflation happen, and still having this amount of asymmetry after inflation. All right, so while this is the lazy person solution, it really doesn't seem to make any sense. You could imagine some more elaborate situation. Here, we just imagine we started out with baryons and antibaryons mixed in with each other and waited till their interactions froze out to set the asymmetries. But you could just imagine that the universe was started in a special way where all the baryons were over here and all the antibaryons were over here, and they just, because they're in spatially different places, they never got together to annihilate, right? So if we just happen to live in the baryon-rich portion of the universe, then we would see a universe that apparently had this baryon asymmetry. All right, that's also disfavored by data, basically because you can still go and look if there were baryons and antibaryons in different places. you can still go, you can look for reactions where they would be annihilating together efficiently, where there's some large population of antibaryons. We don't see any evidence for that. So if this is what happened, the antibaryons really have to be put some crazy place where we don't see them. So that seems also a little unnatural. All right. Okay, so that leads you to the last possibility. Maybe this asymmetry is a result of some dynamical process in the early universe. All right. So I think everyone has seen, hopefully at some point, there are conditions which Sakharov worked out that are the conditions that need to be satisfied if you want to start in a universe that is symmetric between baryons and antibaryons, and you want some dynamical process to end up giving you more baryons than antibaryons. So you need three things to be satisfied. The first is you need baryon number to be violated, right? So that's because if you started from a situation where you had no difference in the number of baryons and antibaryons, if you want to get a number of baryons out that's different from 0, you better violate baryon number. Okay, so baryon number has to be violated. You have to violate both C and CP, okay? If either charge or charge parity is a completely good symmetry of your theory, then any process that you would have that creates baryons, you could use a C transformation or a CP transformation to also create antibaryons. So in order to get, again, an asymmetry, you need to violate both C and CP. Okay. And finally, you need to get a departure from thermal equilibrium. Basically, the reason for that is you need a direction in which processes can proceed from a completely baryon-antibaryon symmetric stage to a baryon-antibaryon asymmetric stage. That requires a sort of direction in your processes, which corresponds to a departure from thermal equilibrium. Okay. So those are the requirements. Now, what's very suggestive if you just look at the standard model is we get this close to doing it in the standard model with nothing extra. Okay, that would be fantastic if it really worked. How do we get that close? Okay, so to satisfy the first condition that there's some baryon number violation, there are non-perturbative configurations in the electroweak sector of the standard model, sphalerons that violate baryon number, and you can use them, or you could also use them. They violate separately baryon number and lepton number. So if you're in a condition in the early universe where these phaleron configurations are produced efficiently, then you can use that as a source of baryon number violation that could then shut off at later times. Okay, so the standard model could, in principle, give you this baryon number violation from these non-perturbative field configurations. Now, we already know that we have CP violation in the CKM matrix. Okay, so we satisfy CKM violation. The C violation takes a second to explain. So these are conditions that aren't generally violated in equilibrium in the standard model, but they could be satisfied during the electroweak phase transition. So the idea behind the electroweak phase transition is, okay, we know, the one-dimensional projection of the Mexican hat potential for the Higgs, right, at the origin is not actually stable. The actual stable minima for the Higgs potential lie away from the origin. And so this is something that gives us spontaneous, at 0 temperature, spontaneous violation of electroweak symmetry. Now, that's the 0 temperature potential for the Higgs. But if we turn on, if we go to finite temperature, we turn on thermal corrections, what actually happens then, of course, we get finite temperature corrections to the effective potential for the Higgs. And at some higher temperature, actually, the minimum of the finite temperature effective potential is actually at the origin of field space for the Higgs. Okay? So the finite temperature at very high temperatures, the finite temperature potential gives us a symmetric minimum where electroweak symmetry is preserved. So then, of course, what happens is you cool the universe down, is the finite temperature piece gets less and less important. Eventually, it starts to compete with the 0 temperature piece. And so you can end up in a situation where from a symmetric minimum, you evolve minima away from the origin. Okay. Now, there's two different possibilities for how this could occur. It depends basically on the competition between the thermal pieces and the 0 temperature pieces. So the two ways that it could occur, one would be a first order phase transition. So in a first order phase transition, these other minima form well away from the origin, still while you're pinned near the origin. So in a first order phase transition, you would undergo tunneling from the symmetric phase at the origin to one of these minima away from the origin. Okay, so you would nucleate bubbles of the new phase. Those bubbles would expand at the speed of light, and they would eventually fill up the universe in the broken phase of electroweak symmetry. The second possibility is that these new minima evolve smoothly from the minima at the origin. So if the potential just flattens out slowly and then develops these bumps, then if you started out at the minimum here, you would stay at the minimum here, and then eventually you would roll down very smoothly to the new minimum away from the origin. So that would be a second order phase transition, right? You're just smoothly being deformed away from the origin. You don't nucleate bubbles of a new phase. There's no tunneling processes. It's a very smooth and non-violent transition. Okay, so sorry for that very brief introduction to the electroweak phase transition. I think that's all we need to understand the physics here. Okay, so during the electroweak phase transition could help you with baryogenesis if it were the first type, if it were a first order phase transition, where your transition to the symmetry breaking phase were due to the nucleation of bubbles of the asymmetric vacuum that then expanded in the universe that was previously symmetric. Okay. And the reason for that is these bubbles expand, they have domain walls that interpolate between the symmetric phase outside and the asymmetric phase inside, and those domain walls actually break charge, they break the charge symmetry of the standard model. Okay, so if you have a situation where you have those domain walls expanding around these bubbles, that would break C. CP is already violated in the standard model, so together those two things would break C and CP. All right, and then the final condition, departure from thermal equilibrium, if the phase transition is strongly first order, that's nucleating these bubbles of the phase, having them expand, that's a strong violation of thermal equilibrium. That's very much an out of equilibrium process, so you would also satisfy the third Sakharov condition. So we get really close in the standard model during the electroweak phase transition to actually having all the things we need to make the baryon asymmetry. So in principle, it all works. In practice, it doesn't. There's never quite enough of anything. So in particular, we have CP violation from the CKM phase, but the way that it would appear in processes that would generate a baryon asymmetry is far too small. Okay, so you never get enough CP violation coming from the standard model. The other problem is now that we know the Higgs mass, all right, we know, at least in the standard model, we know exactly what the Higgs potential should be. And given what the Higgs potential is, in the standard model, then we can actually ask, is the phase transition first order or second order? Okay, and the answer is, if the Higgs is at 125 GeV, and there's nothing else in the theory but the standard model, then we actually know the phase transition is second order. Okay. All right, so we got close, but we didn't quite get enough. So again, what do model builders do? There's a good idea. It seemed really like it was about to work. It just fell a little bit short. So you ask, okay, what additional ingredients could I add to my theory that would satisfy these conditions that explain why we have more baryons than antibaryons? Okay, there are lots of models of baryogenesis. I don't want to go in detail to any of these, but I do want to tell you the sense in which there are many possible explanations, and they're all very interesting. So one of which, the first idea is just to say, look, we got close to getting a baryon asymmetry in the standard model just from the electroweak phase transition. The only reason it failed was we didn't quite have enough CP violation, and with the Higgs that we see, just in the standard model, the phase transition is not strongly first order. Okay, so there's a simple thing to do, right? There's a simple thing to say, look, I need to make the phase transition first order. It's not first order in the standard model, but if I added new particles that coupled to the Higgs, that would actually change the form of the thermal effective potential. Right? It would change its shape relative to the standard model, and those changes in shape would be larger if the coupling was large. Okay? So if I have new things that couple to the Higgs with some large coupling, then that could alter the effective potential of the Higgs at finite temperature and make sure that the phase transition was actually first order. So then we would get out of equilibrium, and we would get charge violation from these bubble walls. Okay. So that's something possible that you can do. And in particular, also, you could introduce new, so C violation would again just, and CP violation could even be induced by these couplings. So that gives you a sharp prediction, right? It tells you should have new particles. They have to be light in order to affect physics around the phase transition. And they have to have this giant coupling. So those are things that we should be able to see at colliders. All right. Now it's a detailed question. If the new particles have standard model quantum numbers, they actually lead to deviations in Higgs couplings. For example, they change the Higgs couplings to gluons or the Higgs couplings to photons. And also, they change at the end of the day what you would interpret as the Higgs self-coupling by changing the effective Higgs cubic coupling. So this is an interesting idea, right? It's just saving electroweak baryogenesis, but it gives you interesting predictions for new physics at the TeV scale that you should be able to see. All right, there are other ideas that don't necessarily have anything to do with the TeV scale, so I just want to mention them briefly. One is you could connect baryogenesis to whatever physics gave you neutrino masses. That's because the neutrino mass operator violates lepton number, and you can dress up your mechanism for the neutrino masses to satisfy all the Sakharov conditions. So in particular, you could have heavy right-handed neutrinos that gave you this effective operator, and their couplings could violate CP. All right, so if you had those, that would give you the CP violation that you need. If those right-handed neutrinos decay in the early universe, that would be out of equilibrium. That would give you your third criteria. And then we already know we have these sphalerons. The sphalerons would actually convert lepton number violation into baryon number violation, and that would give you condition 1. So that's a way to get baryogenesis out of things connected to neutrino masses, called it leptogenesis. And then there's other ideas, basically, that use, what do I want to say? They use large effective amounts of baryon number violation from the oscillations of fields in the early universe. The mechanism is a little delicate, so I don't want to waste a lot of time on it, but these things are called mechanisms of Affleck-Dine baryogenesis. Okay, so lots of ways to do it. Some of them are connected to things that we already know, like neutrino masses or electroweak baryogenesis, but some of the models could exist on their own. All right, so I just want to tell you a little bit more about how some of these things might be connected in detail to physics at the TeV scale, how this baryon asymmetry that we see in nature could point to new things at a TeV. Okay, so the first thing I just want to spend a little bit more time on is this notion of what would it take to save electroweak baryogenesis. So what new particles would have to couple to the Higgs in order to make the electroweak phase transition strongly first order. All right, so we have to introduce some new particles. They have to have a big coupling, and they have to be light near the weak scale so that they are important for the thermal effective potential of the Higgs at the electroweak scale. All right, so again, if these new particles are charged and colored, it's an easy game to look for them because we just produce them, for example, through their color or through their charge. So for example, you could imagine adding some new particle. Let's say it carries color and hypercharge. That would have the same quantum numbers as some of the, for example, the partners of the top quark that we get in supersymmetry. And then you can ask, okay, what size does the coupling have to be and the mass of the particle have to be in order to make the electroweak phase transition strongly first order. So you can go ahead and make a plot of that, and basically there's a region of parameter space. The couplings have to be big, larger than 1. The masses have to be small, beneath about 500 GeV. And so there's some band where you can get electroweak baryogenesis to work. But that means you're predicting a new particle that couples to the Higgs, that has standard model quantum numbers, and it has a large coupling. And so that means it gives quantum corrections to Higgs properties. So wherever you make electroweak baryogenesis work with this new particle, you also change the Higgs properties in a way that you would see in Higgs coupling deviations. All right. So what's the moral of this story? Again, it takes just a little bit to save the idea of electroweak baryogenesis, but it gives you a very strong reason to expect new particles that are showing up at the TeV scale and that have couplings to the standard model, so we should be able to see them. Okay, again, this problem had nothing to do with the hierarchy problem, had nothing to do with strong CP problem, unification, but it's still pointing to new physics showing up at the TeV scale. All right, let me give you a second example that's a little bit wilder. So this is something that was called wimpy baryogenesis. Okay, so this is a very different idea about how you could generate the baryon asymmetry, but it has a little bit to do with what you've learned about dark matter earlier this week. So let's imagine that I have a new particle in the early universe that in many respects is like dark matter. So I don't want it to be dark matter. I don't want it to be around today explaining dark matter as we see it. But I want it to get some abundance in the early universe from the same thermal processes that give me the abundance of dark matter. Right? So in particular, if I have this new particle in the early universe, all right, it can be annihilating away in the early universe, but eventually the expansion of the universe makes those annihilations inefficient and leaves behind some thermal relic abundance. All right, so I can have this new particle, I can get an abundance of it in the early universe by freeze out, just like dark matter. But I don't want it to be dark matter. I want it to be unstable, and I want it to decay. All right. Now, its lifetime can be long, right? So it gets some abundance, and then it decays. And if it does that, it gets its abundance, so there's a lot of it sitting around in the universe, and then it decays. And if its decays satisfy the rest of the Sakharov conditions, then I can use that to generate my baryon asymmetry, right? I can use that to produce baryons, and the number of baryons I get is going to be proportional to the number of these particles that I had from a freeze-out process. And that seems like a really good idea. Well, I don't know how much it was emphasized in your lectures about dark matter, but the amount of dark matter, right, the energy density in dark matter is about 5 times that of baryons. So these numbers are very close. right? So that's a suggestion that maybe they're related, right? So if, for example, I had a mechanism that gave me about a dark matter's worth of abundance of a particle, and then I had it decaying to give me baryons, right? That would be coincidental. That coincidence would be about right? So if this thing were a weak scale particle, it had a weak scale dark matter relic abundance, then it decayed to baryons, that would give me about the right number of baryons. So that's why this is an attractive idea, right? It explains in some natural sense why the abundance of dark matter that could come from a thermal process would be similar to the relative abundance of baryons. Okay. So the way, again, a cartoon form of how this would work is, in the early universe, this particle, let's call it chi, it annihilates into standard model particles when it's in thermal equilibrium. Eventually, the universe expands, that process becomes inefficient, these guys freeze out. And then at some later time, right, these things go ahead and they decay. And if their decays violate CP, and if they violate either baryon or lepton number, right, then we satisfy all of the Sakharov conditions. The decay is out of equilibrium. If the couplings violate CP and baryon or lepton number, then we satisfy the violation of baryon number and CP violation. Okay, so this would be a way to make more baryons and antibaryons. And what's fun about this, right, these are the things that you need for the story to work. You need it to be able to annihilate to the standard model in the early universe. Then once you have some thermal abundance left over, it has to decay. So that sets the strength of the couplings to the standard model, both for this process to work and for the lifetime of the particle to be long enough for its decay. So what's great about that is, and also, again, to get the right amount of this stuff, it has to be like dark matter, it has to be around the weak scale with weak scale couplings. So you put all those ingredients together, and you get an interesting prediction for what might happen at colliders, right? That you have to have this process to get the freeze out of the dark matter. So of course you can reverse the process, and if you smash protons together, you can produce these guys. And now the process that leads these things to decay into the standard model to generate the baryon asymmetry, if I produce these guys at a collider, they should decay to standard model particles. But because this process has to happen well after this occurs, this coupling is pretty small. And what that means is, at the LHC, when you produce these, they travel some finite distance, at least more than a millimeter, before they actually decay to standard model particles. So this gives you a really cool prediction, right? It tells you that if these are the things that are responsible for generating the baryon asymmetry, first thing is you should be able to produce them at the LHC, because they should be light enough and they should have couplings to the standard model. And the second thing is whatever decays allowed them to generate the baryon asymmetry tell you that they will travel for some distance at the LHC before they decay. So you get a very interesting signature of displaced objects at the LHC, all right, which is a very exotic signature and one that we haven't really looked for optimally at the LHC so far. So there are lots of cool searches for displaced objects at the LHC. Basically what you look for, you really do look for vertices that show up away from the original collision point. The details of these searches are very intricate, and again, it's heroic effort on the part of the experimentalists to do this well. But this is a real growth direction in terms of signatures at the LHC, just because we didn't build the LHC detectors to look for this stuff, right? When we built the LHC detectors, we built them to look for Higgs bosons decaying promptly, and we built them to look for things like supersymmetry, again, where everything happens right at the interaction point. We did not build them to look for particles that get produced and travel a meter and then go poof. Okay, so it's an interesting process at the LHC now to come up with good ways to search for these particles. Again, what's the takeaway? We have evidence for something new, the fact that we have more baryons and antibaryons. We can't explain it just using the standard model alone. There are lots of ways we could explain it. So not all of those ways would we ever have experimental access to, but there are some really interesting ways that sort of jive nicely with the data that we have, where the new physics would appear at the TeV scale, would be accessible to us at accelerators, and it would give us interesting new signatures. All right. Okay, so what we've now gone through, we've covered a lot of ground, right? So we've talked about maybe 1,000 solutions to the hierarchy problem. We've talked about ways to solve the strong CP problem that are related to the TeV scale. We've talked about how unification could show up at a TeV. We talked about how you could generate the baryon asymmetry at a TeV. Of course, there's a lot more that we haven't had time to talk about, and obviously there are connections between dark matter and neutrino mass in the TeV scale. So anything, we have these reasons to think there's physics beyond the standard model. The reasons for it range from purely theoretical to at least suggestive based on current evidence to absolutely unavoidable. And all of them have manifestations that can show up in interesting ways at the TeV scale. So what I've tried to do in these lectures is not tell you how to do detailed calculations, because you can always figure out how to do detailed calculations in your office. What I've really tried to communicate to you is the sense of richness of possibilities for physics beyond the standard model, and how these possibilities can connect in interesting ways to the TeV scale, which coincidentally is the energy scale that we're now capable of probing at colliders and other experiments. But the other thing that I've hopefully convinced you of is that, we've had these problems for a long time. There were a lot of solutions to the problems that became very dominant in the theoretical physics community. But now that we're testing those ideas and they haven't shown up, it's a really good time to expand your mind. The problems are still there, right? But we probably haven't written down the correct theoretical explanations yet. So this is where you guys come in. And the important thing is to understand in a useful way what the problems really are, so that you can start to think about what new solutions might be out there. So what I've tried to do, hopefully, is at least give you some inspiration for thinking in those directions. Now, I just want to end by looking a little bit towards the future. So we have the LHC now. The LHC is going to be going on and collecting data for quite some time. But we are in a funny period where we've made the last big leap in energy that the LHC is going to make. And so now all we have to do is integrate more collisions and hope that that gives us something surprising. But thankfully, you guys are all young people, and so you have a much brighter future ahead of you than just the rest of the LHC. So what I do in my free time, when I'm not thinking about things that are more connected to the TeV scale, is try to help make the case for the next generation of colliders. And starting in about 2013, when a lot of different people started talking in a serious way about pushing this effort forward, a lot of these ideas seemed completely crazy. But now in 2017, we're in a period where it seems like some of these ideas might actually happen. And all of these ideas would happen on timescales that are useful for you and for your careers in physics. So, of course, for a long time, we've had the proposal of an international linear collider. The primary purpose of that originally was to look for supersymmetric particles, but now people have sort of reconfigured their thinking to understand the sense in which this might be good for understanding the Higgs boson very precisely, and using that as a way of probing, for example, all of the possible operators in the standard model EFT. So the ILC, the ILC has been in limbo for a long time, but thanks to some recent restaging proposals, there's a non-zero likelihood that the Japanese government could approve the ILC within the next year. And the ILC, as a technical proposal, is already complete. So as soon as it got approved, they could start digging, right? And we could, within the span of a decade, have an interesting new linear collider that could probe Higgs properties with a precision we have yet to obtain. There are also lots of interesting proposals now for circular colliders. So I spent time working on both of these, but maybe more so on the Chinese proposal. So there's a proposal for the Chinese to start by building a circular collider that would first collide electrons and positrons, just to be a Higgs factory. So again, probe the Higgs with unprecedented precision. But again, much like we had LEP and then we built the LHC, if you dug that tunnel for the E plus E minus machine, you could fill it with superconducting magnets and eventually build a proton-proton machine. And if you put it in a ring that was 50 to 100 kilometers, you would get a 50 to 100 TeV proton-proton machine, which would allow us to make another order of magnitude leap in the center of mass energy. Okay, so that proposal is still in progress. There's R&D work that's happening for CEPC now. We sort of have to wait and see what the Chinese government is going to do. But within the next few years, Chinese research funding should exceed research funding in the United States. So things are moving in the right direction for the Chinese. And then, of course, at CERN, there are a lot of ideas. So CLIC has been around for a bit of time. This would be a higher energy linear accelerator than the ILC. The CLIC effort is still very lively. That would probe even higher energies in a very precise environment. But the thing that's really moving very quickly now are proposals at CERN to build a future E plus E minus machine. And much like the Chinese proposal, the idea would be to start with the Higgs factory and then eventually upgrade it to a proton-proton machine. This seems like a direction that CERN is interested very seriously in going in. Of course, it would have to wait till the LHC itself finished to really get going, but that's something that's still relevant for the lifetime of your careers. So I just want to emphasize, I'm giving you these lectures about BSM physics at the TeV scale, but on time scales that are relevant for your careers, right? When you're here giving these lectures in 10 years or 20 years, or 5 years if you do really well, you could be talking not about BSM physics at the TeV scale, but BSM physics at the 10 TeV scale or the 100 TeV scale. And many of the reasons that we're excited about physics at the TeV scale are even more exciting at higher scales. And it'll be a really exciting time if one of these experiments gets off the ground to see what we can learn from it. So there's a bright future ahead. I mean, there's bright futures in every direction, whether it's probing things at the sensitivity frontier, like Andy told you about, whether it's probing things in the cosmological frontier, like you've heard about in several of your lectures. But if you're interested in probing things at the energy frontier, there are a lot of exciting proposals, and in the next few years, some of these might start to become reality. So there's a lot to look forward to, and hope that you enjoy the experience. Okay, so with this, I want to conclude. Hopefully, I've convinced you in my 4 lectures that there is a huge abundance of motivation to think about new physics at the TeV scale, extending the standard model, both from things that we think of as conventional drivers of physics beyond the standard model, like the hierarchy problem, but also less conventional ones. So I told you about how the strong CP problem could give you new physics at the weak scale, unification could, baryogenesis could, and then of course, hopefully you've also heard about how dark matter and neutrinos could also give you new particles at a TeV. So we've had a long time to start thinking about these ideas. There are a lot of popular ones, but those solutions, again, I just want to emphasize, those popular solutions are being tested, and we have yet to find any evidence for them. So from your perspective, this is a good time to start thinking about new ideas. And you shouldn't feel bound or constrained to what's historically been popular. And I think within the next few years, we're really going to start to see the field of theoretical particle physics changing, in the sense that people are going to be pursuing more adventurous ideas because data has yet to validate the ones that we've already proposed. All right. Many of the signals of all these theories are only now coming into the reach of colliders and other TeV scale probes, and we have a lot to look forward to both at the LHC and at future experiments. So thank you so much for your time. It's been a real pleasure to talk to you.